Okay, here we go. So this is the circulation version. And I like to start off with this because Stokes is going to be the 3D version for circulation. Now, in this circulation version, which is greens, you don't really have a three-dimensional vector field. You have a two-dimensional vector field, essentially, with just M and N. But if you think of embedding the two-dimensional vector field into 3 dimensions, then you can think of that third component of your vector field being 0. Fine. So this higher dimension analog of greens is called Stokes, and it's named after a mathematical physicist named George Gabriel Stokes. And so this is the way that Stokes works. It gives you a relationship between the surface integral and a line integral. Okay, which is very cool. Now, greens gave you the relationship between not a surface integral, but a regular double integral and a line integral. So we're going to do somewhat of a similar thing. So here's greens. This is a little picture. You're looking at the boundary here of a region, and you're going in the counterclockwise direction, and you're getting the circulation. And this right here is your curl of F, two-dimensional, but three-dimensional if you consider this dot product with the K unit standard vector. And so what Stokes is going to do, it's going to hit it in 3D. So instead of a flat region here, if you can imagine the region like getting kind of blown up and being a surface, you're going to compute the circulation around this boundary of this surface like that. And you're going to get this circulation here. Isaiah, did you have a question? No? Okay. Never mind. I'm going to mute you. Okay. So Stokes is going to go, all right, I want the circulation, which is this line integral. And you're going to do a surface integral instead of a regular double integral. And you're still going to find a curl here, curl of F. But instead of taking the dot product with K hat, which is just 0, 0, 1, you're going to take it with an outwardly directed unit normal vector N from the surface, okay? And sometimes they might be called large capital N, depends on your textbook. Okay, so here's the right-hand rule. So physics folks, here you go. You remember the right-hand rule when we took cross product? Well,
Yeah.
we use the right-hand rule again, not for doing a cross product, but for figuring out the direction that your unit normal vector is. So when you circle your fingers around the curve, which is sort of the border of the surface, then stick your thumb up, and your thumb is pointing in the direction of N, okay? And your fingers are pointing in the direction of positive direction for C is shown in the figure, okay? So here's Stokes right here. Officially, here's Stokes. You got an oriented surface with a unit normal N bounded by a piecewise smooth, simple closed curve with a positive orientation. That means counterclockwise. And if F's a vector field whose component functions have continuous partials on an open region containing the surface and the curve, then this line integral can be converted to a surface integral. Now, you know how to do surface integrals because you're going to have a midterm on Wednesday for it, but also because that's what we did in section 17.6. We did surface integrals when we were computing flux. But now we're going to have a surface integral to help us compute circulation, different from flux, okay? Different from flux. So I'm going to do an example. And then I'm going to put you in groups, and you're going to do an example with your buddy. Sounds good, right? And just follow my lead. So if you understand what I'm doing in this next example here, example 1, you will do fine on the very next example. Okay, so just follow the procedure. Okay, so they want us to use Stokes to obtain a circulation if we let the curve C be the oriented triangle lying in the plane given by 2x plus 2y plus z equals 6. So I hope you can see that the overall curve is going to be C1 union C2 union C3, which are the legs of this triangle. That's your curve. And you're trying to get the circulation around that triangular curve. And it is piecewise smooth. So that's good news. Cool. Now, if you had to do a line integral here, you'd actually have to do 3 separate line integrals and add the results. And that would be one way to do it if you were asked to do a verify, say. But the claim is that I don't have to do this left-hand side with 3 separate line integrals. I'm going to do one surface integral. So that's what I'm going to do here. So one of the ingredients of that surface integral is I got to go get the curl of the vector field. Good news. You know how to find curl of a vector field. That's also going to be on the midterm 4. Okay. So how do you get the curl of F? And I appreciate it. Otherwise you'll lose points if you do it the way I want you to, which is the 3D determinant method. I want to see this on your paper. If I don't, well, I like just to use the formulas. I don't want you to, because now we're online and remote and you have access to all your notes and whatever. But in the future, you may have a physics teacher who doesn't let you have any notes or books or whatever when we get face to face. But you can always easily derive your curl if you follow my lead and you use the 3x3 determinant method. And this is why I'm a little bit hardcore about you doing it this way. I hat, J hat, and K hat across the top. The differential operator, which is you can think of as a hollow vector, ddx, ddy, ddz, those components go along the second row. And then the vector fields components along the bottom row, where your vector field is given. And then you're going to do the 3x3 determinant method. You're going to have a 2x2 determinant method multiplied with I hat, minus 2x2 j hat plus 2x2 determinant times k hat, all that. So this first thing is going to be d dy ddz xyz e to the z. The second one, block out the row and column that j hat lives in, and you get ddx ddz, and then the bottom row 2y minus z e to the z. Last 2x2 determinant, block out the row and column that k hat lives in, you get ddx ddy, 2y minus z, xyz. Okay, and then you're going to go like this. Okay, you think of multiplying the major diagonal, which is going to be for us, take the partial with respect to y of e to the z, minus take the partial with respect to z of xyz, and then multiply that mess by I hat, minus this one says take the partial with respect to x of e to the z, minus minor diagonal, take the partial with respect to z of 2y minus z, and then multiply that by j hat. And then finally, take the partial with respect to x of xyz, minus take the partial with respect to y of 2y minus z. Okay. A lot of partials. Here we go. So what is partial with respect to y of e to the z?
0.
0. And then partial of xyz with respect to z?
xy.
xy. And that'll be I hat. Minus ddx of e to the z?
0.
Yeah. And then ddz of 2y minus z, that's going to be -1. And then you have j hat here. And lastly, take the partial of xyz with respect to x. I get yz minus the partial with respect to y of 2y minus z. And that is going to be what? Just 2. Okay, and then k hat. And then I'm going to put this in component form and do a little bit of cleanup. So the first component is going to be -xy. The second component, ooh, we got a lot of negatives floating around. This minus minus turns into a plus, but then you distribute this minus, so I'm going to get -1. Ooh. And then yz minus 2 is the last component. Now, if when you're doing Stokes, you at least get the curl, I'll give you like 1 point out of 25. Well, I think it's actually 50 points. It's going to be like 1,000 something point, I think 1,010, I forget, points total on your final. I know, right? But I mean, I'm going to grade it over 100% or whatever. When I post it in Canvas, you'll see the 100%. But the Stokes problem on there is going to be like a full half a letter grade. So if you think, oh, well, I know they're doing Stokes today, screw it, I'm not going to study it. You want to study Stokes, because the one Stokes problem I'm putting on the final, full half a letter grade. Yeah. So know how to do it. It's not that hard. Okay, you get your curl. Then what? You're going to get your unit normal vector. And we talked about getting this from last week. We want the outward and upward unit normal vector. So it's going to be minus gx minus gy positive 1. But what's little g for this problem? Anybody see it?
It's a plane
It's
equation.
going to be the plane equation.
Yeah.
Or you could just set z equal to g and then
Solve for z, right?
Exactly.
Mm-hmm. So you're going to have to do that because they didn't give you the surface equation explicitly, but you all know how to do that. And so 6 minus 2x minus 2y, what's the partial of this with respect to x?
It's 2.
2x. Or sorry, 2.
I think it's negative 2.
Negative 2.
How about the partial with respect to y?
Yeah, you're right. Negative y or negative 2.
Negative 2. So careful, this is where students lose a whole half a letter grade because they screw up their negatives. You know, and I'm not very nice about it. Like I'm not going to go, well, I'll just take away 1 point and give it to you. You're going to go negative, and then the partial with respect to x was negative 2x. And then negative, negative 2, sorry. Negative 2. And then negative, and the partial with respect to y was also a negative 2. And then we have the 1. And then negative negatives are really positives. So this is our n. So now the circulation that we're trying to find is this surface integral where you're going to take the curl of f and dot product that with n ds. And remember that the n's, when you unitize it, the magnitude cancels with the surface area element. So you don't even worry about this surface area element when you're doing one of these surface integrals. So you turn it into a regular double integral where the projection of the surface onto the xy plane, which we're going to call r. And then we got this curl, negative xy, negative 1, yz minus 2. And you're going to take the dot product of that with 2, 2, 1. And so let's do that dot product first. So you're going to go, okay, negative xy times 2, that's negative 2xy. Negative 1 times 2 is negative 2 plus yz minus 2 times 1. Okay, that's just going to be yz minus 2. Okay, and now you get to pick, like, do you want dy dx or dx dy for your order of integration? I like dy dx. And then what is the projection of this surface onto the xy plane? Well, the region R is this triangular region down here in the xy plane. And you know, since this particular capping surface, it's kind of slanted there, it cuts into the xy plane. If you set z equal to 0, you'll see the trace of it on the xy plane. So the graph of 2x plus 2y equals 6. I do it over here. Here's our region. 2x plus 2y equals 6. I think that the intersection, the x and y intercepts are 3s. So this is the graph right here of 2x plus 2y equals 6. And it's here in the first quadrant. And so you'll probably want to solve this for y. And when I do, I get y is equal to 6 minus 2x all over 2. But I can reduce this to lowest terms. Y equals 3 minus x. So why is that important? Because when I iterate this double integral, I'm going to get 0 to 3 for the limits on x and 0 to 3 minus x for the limits on y. And if I were you, I would do a couple things before you integrate. One thing that I hope that you see right off the bat is when you're doing a double integral, you're really only allowed to see 2 variables, in this case, x's and y's, but I have a z there. What do I do with the z?
Replace it.
Yeah, what do I replace it with?
Planar equation.
6 minus 2x minus 2y.
Yeah, it's the plane equation, 6 minus 2x minus 2y. So you better do that. And now some easy Stokes problems will have your vector field won't have any z's in it, and you'll get lucky where you won't have to do a replace. And you're like, oh, I don't have to do a replace. But you know what? I try to find problems, not only on my homework and my exams, hint, hint, where there will be a z that you have to worry about and replace on flux integrals or, and so on. So please know how to do that because that's super important. Now I'm going to do a little bit of cleanup before I integrate with respect to y, because I'm going to combine these negative 2's and then I'm also going to do the replace. I have negative 2xy minus 4 plus y times this 6 minus 2x minus 2y guy here, like this. Oh, man. And then what? Well, if I were you, I would distribute your y before you start integrating because, you know, otherwise you'll run into a problem. It won't give you the right answer. And then you are going to do this by hand. And, you know, this is the part where I hope, because you had so much multiple integration in my class, that you would, you know, this is like the easy part. So I'm going to distribute my y. What am I doing here? I got minus 2xy. Yeah, another minus 2xy, and then minus 4y squared. No, minus 2y squared, sorry. I'm going to combine like terms again because these two guys are alike and they combine to negative 4xy, and then I'll integrate. And then when I integrate all of these terms, I'll get, let's see, so this is minus 4xy, I'll get minus 2xy squared minus 4y plus 3y squared, and then minus 2/3 y to the third, going from 0 to 3 minus x. Okay, this is going to get really messy because, you know, you're going to go, minus 2x times 3 minus x squared minus 4 times 3 minus x plus 3 times 3 minus x squared minus 2/3 3 minus x cubed. That's looking terrible. Okay, I'm just going to go et cetera, et cetera. Right now it's a calculus 1 problem. This is where you just call one of your calc 1 buddies and tell them to go do it. I get negative 18. And what does that mean? If you had one of these paddle wheels and you now have 3 dimensions, not 2, so you have like vector field is a jacuzzi, water flowing around, your paddle wheel would spin in the clockwise direction around that rectangular, or excuse me, triangular curve. Negative 18. Okay, so what's the point? This is the 3D version of the circulation form of Green's, and you're finding circulation in 3D. That's all. And then here's a t-shirt you can go buy. Stoked. Yeah, okay. So you and a buddy are going to do example 2. And so what is it? Let's just tee it up before we throw you into some breakout rooms. You're going to use Stokes to compute this line integral, circulation line integral, where the curve is similar to what I just did. It's going to be a boundary of the part of the plane, 2x plus y plus 2z equals 2 in the first octant, oriented counterclockwise. And they're showing you a picture right here. So when you view it from above, it is going clockwise. So if you can imagine your hand with your fingers curling around in this direction, your thumb is going to be like sticking out of that triangle. So your thumb is going to be pointing in the direction of the unit normal vector. And that's the point. Okay. So you have all the knowledge. This is your vector field. It's a little different from mine, but it's very similar. So I'm going to, let's see, how many people do we have here? 7 breakout rooms and throw you in. Okay, and I'm going to come visit your breakout room, so we'll see you soon, okay?
Alrighty.
Have fun. Okay, so did anybody get the answer? What do we get here? What's the
Got an
circulation?
answer. I'm not sure if it's right.
Okay, well, you know, just have a go at it. 3/2 is correct. So this is the answer, 3/2, which is choice letter D. So how'd that work? Well, if you did all this, this was actually a very, very easy problem, easier than the one I did on the previous page, because why? Well, it turned out that the curl of f, after you setting up, you know, I hat, ooh, hold on a quick second. I'm having a power problem. Let's see if that fixes the problem. Yeah, it does. God, that makes no sense. Whatever. Microsoft Surface. Ugh, the worst. So if you had put your 3x3 determinant ready here, you have what? Z plus x cubed sine x for your first component, and then e to the y for your second, and then negative 2x. So if you want to kind of do this on the fly, you're going to go, you know, something times I hat. So you're going to go d dy of negative 2x, that's 0, minus d dz of e to the y, that's 0. Minus, and this is the part where, oh, I don't know what just happened. Huh, that's weird. Why is my eraser not working? Let's try this. Okay, hang on. I'm gonna pause. So if you did your curl okay, this is your curl, right? So I'll give you 1 point out of 50 if you got that far. Woohoo! Congratulations. Now what? You need to get your unit normal vector, the NDS portion, which is essentially negative gx, negative gy, 1. But what's our little g? Well, they gave you that plane equation. So if you did solve it for z by first subtracting 2x and y from both sides, and then multiplying both sides by a half, like this, there's your little g, like this. And so if you go, okay, what's the first partial of that with respect to x? Well, the 1/2 is still there. And then when you multiply by whatever the partial of negative 2x is with respect to x, you get that. But that's going to be negative 1. And then little gy is 1/2 times negative 1, which is negative 1/2. So if you come down here and you're going to go negative gx, you're going to go, okay, negative negative 1, and then negative negative 1/2. See all these negatives floating around? It can be quite confusing. So you're going to use 1, 1/2, and 1, and that's the vector that's pointing upward and outward. And now by Stokes, you can say the following has to be true, that this line integral, which we don't have to do because we now know Stokes, you can turn that into a surface integral, and you're going to take the curl of f dot product with the NDS. And so you're going to go, I'll turn that into a regular double integral. And so your curl was 0, 3, 0, and the dot product with 1, 1/2, 1, and then dA. And this is a super easy dot product to take because you're just going to end up with 3/2 because your curl was a constant vector. We call this a constant vector. And do you always have your curl being a constant vector? Oh, heck no. You can have your curl have x's, y's, z's, and all sorts of stuff in it. If you get lucky, you could get a curl this nice as a constant vector. And we got lucky. Now what? There's 2 ways to do the rest of this problem. And I want to show you both ways because on an exam, I want you to be able to do either way. So let's do the easy way. Way number 1, and way number 1 is great, and I'm totally okay with it. Since 3/2 is just a constant multiple, I'll pull it out of the double integral. And what do you know from double integrals that have a 1 as their integrand? What do they represent?
Area of the region.
Yeah, area of the region. And in this case, the region is a rectangle. So it's just going to be area of a triangle. And triangles have areas that are 1/2 base times height. So if you look at the projection of this surface onto the XY plane, this is your region R right here. And if you look at the, if you set Z equal to 0 here, you'll get y plus 2x plus y, sorry, I'm looking at the plane equation over here, 2x plus y equals 2. So the y-intercept is 2 and the x-intercept is 1. And so, well, that's a terrible looking triangle, but I think you get the idea. So this down here will be the base, and this is the height. So if area is equal to 1/2 base times height, you're going to have 1/2 1 times 2, and I get 1 square unit is the area of our triangle. Wow, that's easy. Does it always get that easy? No. So final answer here is 3/2 times 1, which is 3/2, and that is the answer. Now, way number 2 would be where, okay, let's say you were, you're taking a test, you're not thinking clearly, and you're like, okay, 3/2 times this double integral. I guess I'll go iterate the double integral. No problem. You can do it. If you forgot that, it represents area. So if I choose dy dx as my favorite order of integration, and I go back to this region here, where this line here is 2 minus 2x, it looks like x is going from 0 to 1 for the limits. And y is going from 0 to 2 minus 2x. And then you can continue, et cetera, and just, go ahead and evaluate that double integral representing area, multiplying it by 3/2. And you still should get 3/2 as your final answer. Okay, so it's up to you how you want to roll there. And I'll let you do the shortcut if you're doing it legitimately. Questions? Is everybody okay with this? Stokes?
Straightforward.
Stokes.
Pretty easy, right? You're stoked? Okay, I'm going to do one more problem. I'm going to do a verify. And this is good review for the fact that you're going to be asked to do a verify of greens on Wednesday's exam. So you want to know how to verify something. When somebody says verify, you should immediately go, uh-oh, because that means a lot of work. It means that if you've got an equation, you have to do the left-hand side, get some answer, and then you got to go do the whole thing over again, do the whole right-hand side. And then the answers better match, because if they don't, you screwed up. Oh dear. Let's hope that doesn't happen. Okay. So this is the verify Stokes. Okay, so we're going to verify. That means left-hand side and right-hand side. So when I say left-hand side and right-hand side, what left-hand side, right-hand side am I even referring to? We'll go back to the Stokes theorem up here, and the left-hand side is an actual line integral. So we're going to do a line integral by brute force. You know how to do this because I've done lots of line integrals for you over the last 3 weeks or so. And then the right-hand side is actually using Stokes, and you get to do the surface integral to go find the circulation. Fine. Okay. Left-hand side, right-hand side. So this is a good review for the midterm, because the midterm, I'm not going to have you do Stokes. You're not going to have anything involving Stokes. But I will ask you to do a lot of line integrals. So this is always good review. Okay, so what do we have here for so Microsoft doesn't mess up? We're going to obtain the circulation where the surface is going to be different now. It's going to be the hemisphere, x squared plus y squared plus z squared equals 4 for z greater than or equal to 0. I want to draw that so you can see the curve that we're working with. So the upper hemisphere centered at the origin of radius 2, like this. I don't know, well, that looks pretty bad. And so what is the curve that we're doing? Well, the curve is the trace that the hemisphere is going to make in the XY plane. So it's just this circle right here in the counterclockwise direction. That's our curl, or our curve rather. So the force field is this guy here. And so fine. So if we do the left-hand side, LHS stands for left-hand side. That means we got to go do this line integral. Yeah. So the first thing we need to do is parameterize the curve. And this is good review because I'm going to ask you to parameterize a circle in your midterm 4 also. Good review for the midterm 4. In 2 days. You got 2 days to get ready, people. So how do you do that? Well, the circle is simply a circle centered at the origin of radius 2, and we're going in the counterclockwise direction. That's important. So it turns out, and you should know this because you had a quiz with this kind of thing on it. You do the radius 2 cos t to sine t, where t time goes from 0 to 2 pi, there is your parameterization of the curve. Boom, done. I'll give you 1 point out of 100 if you, no, these are usually worth, verify is going to be worth 30 points on your exam Wednesday. It's worth a lot. Okay, so now what? Well, if you're actually going to do a line integral, you're going to take a dot product of f with dr. Dr involves, you know, the velocity vector. So you're going to go, okay. Oh, by the way, if you wanted it clockwise, you would just reverse these two components. A clockwise circle would be 2 sine, 2 cos. Okay, now r prime, all right, velocity vector, -2 sine, 2 cos. Okay, and why do we need r prime? Because we're going to do FDR. We're going to do one of these FDR line integrals. Fine. So this line integral here is going to become a regular integral evaluated between 0 and 2 pi. And we're going to take the vector field, which we have to replace all the x's, y's, and z's. Oh, I forgot a z component. Sorry. We're embedding, my bad. What do you think the z component is for being in the xy plane? Exactly. I have my z component here because we're doing 3D. Almost forgot. We're not doing greens. So we've got 0 as our z component. Okay, so we're going to have to worry about replacing the x's, y's, and z's in our vector field with the x, y, and z components that we take from our vector valued function. And we're going to dot that product out with the velocity vector. So I'm just going to copy that guy down right here, 3D, and then dt. Okay, so if you look at the force field, z minus y. So for us, that's going to be 0 minus 2 sine t. And then the middle component is simply x. So that'll be 2 cos t. And the last component is negative x. Okay, that's weird, but okay, fine. All right, now, going to take a dot product. Fine. So you're going to take -2 sine t multiplied with -2 sine t. I get 4 sine squared t. And then you're going to multiply the middle components, 2 cos multiplied with 2 cos. Oh, that's 4 cos squared. Fine. And then you're going to add that to the product of the last components. Yeah, but 0 times anything is 0. Fine. Hey, and then something nice here, because if I factor out the 4, guess what? Sine squared plus cos squared is 1. So this just looks like it's going to be 4 like this, right? Yeah. And so you know the drill. It's just going to be 4t evaluated between 0 and 2 pi, and I get 8 pi. And there's my final answer. Okay, so, but we just did the left-hand side. So we just found out that the circulation is 8 pi. Fine. So now we're going to do the right-hand side, and hopefully it's going to give us the same answer. Now, you're probably not going to like Stokes after you see this right-hand side, because it doesn't make it Stokes look easier for this particular example. And I apologize for that, because normally a verify, you're going to go, oh, Stokes is great. Here, you may not do that so much. So, so the first thing I'm going to do is I'm going to solve for z, because I got to get the surface equation little g. So once I solve for z, which is going to be my little g of xy, you're going to get plus or minus a square root, but because it's the northern hemisphere, you're going to take the positive of the radical. So we'll have z, that's a z, is equal to positive square root of 4 minus x squared minus y squared. And I'm going to rewrite that using exponents, because I'm going to have to go get his partials. So little gx, you're not going to like it, but you know, we got to get it. Using the chain rule, oh boy. Of course this would be, it's going to be 1/2 the quantity 4 minus x squared minus y squared raised to the -1/2 times the derivative of 4 minus x squared minus y squared with respect to x. And that'll be -2x. And when I rewrite this, clean it up, reduce it, and rewrite it with positive exponents, and in fact, I'll replace the positive exponent with the radical, I get that. Now, here's a little trick that you'll see a lot of textbooks do. So don't freak out when I'm doing this, okay? Do you get that this denominator is exactly the same thing as z? Do you notice that?
Yeah.
Just say yes. So I'm going to replace this with z just because it's kind of easier for now, if you don't mind. So just kind of go with this, okay? It's like, I don't like that. I know. And then the partial with respect to y, again, using a chain rule. And then once again, after reducing and rewriting it with positive exponents and replacing the exponent with a radical, I am again going to go, all right, that partial with respect to y, that denominator is the same thing as the z. So basically, negative x over z will be my little gx, and negative y over z will be my gy. Okay, now what? Well, we're going to do this right-hand side, which says, okay, the circulation is going to be this surface integral. We're going to take the curl of the vector field and take the dot product with nds. Okay, fine. But I got to go get the curl. All right. So I have the nds part. Why? Because when I get the nds, it's negative gx, negative gy, positive 1 for an upward and outward orientation. So this is going to be negative x over z, negative y over z, 1. So this is looking like positive x over z, positive y over z, 1. Let's just save that for the moment because we need to go get this. We need to get curl. So curl is going to be, you know, I hat, j hat, k hat, ddx, dy, ddz. And I'm going to have z minus y for the first component, x, and negative x in that order. And then when I go kind of do this on the fly, let's see here like this. So I'm going to go ddy of negative x at 0 minus ddz of x at 0 I hat minus ddx of negative x. Ooh, that's negative 1. Minus ddz of z minus y, that's 1. J hat. Plus, and then I'm going to go ddx of x, and that's 1. Minus ddy of z minus y, that's minus 1. K hat. And then cleaning this up, if I write this in component form, I'm going to need another page. I'm going to have 0, negative 2 is positive 2, 1 minus a minus 1 is positive 2. Okay, so this is my curl. Fine. So let me go put another paper here. This is getting ridiculous. Okay, so here's what we have so far. This double integral, which is going to take curl of f, dot product with n, ds. We're going to turn it into a regular integral over the region, and the region is just that circle in the xy plane. And you're going to take 0, 2, 2, which we just got for curl. Hey, another one of those constant vectors. We got lucky. And then this was our nds x over z, y over z, 1. I know I'm really not allowed to have a z when I'm doing a double integral. I got that part, but hold on a minute. Okay, I have a reason for kind of keeping the z in here just to keep it clean. When I do this dot product, 0 times x over z, that's 0, plus 2 times y over z, okay, that's 2y over z, plus 2 times 1 is 2, okay, fine. And then you guessed it, I'm going to convert to polar. Yeah, because I can. Well, because the region R is this circle of radius 2 centered at the origin. So it makes sense where R is going to go from 0 to 2 and theta will go from 0 to 2 pi. That's how we're going to roll. So when we iterate, okay, now this thing is pretty gross because it's really 2r sine theta. And remember that z, if you look, oh, how do you convert the z? Like if you look at this z, it's square root of 4 minus the quantity x squared plus y squared when we factor out the negative from the x squared and y squared terms. And I hope you can appreciate that that's going to be square root of 4 minus r squared, like this. So that's going to go here. Plus 2, and then you guessed it, r. drd theta. Okay. Now, you're going to distribute this r because you want to do that before you integrate with respect to r. And then I'm going to do something that you may find like offensive, like, oh, I think that was like bogus. And I'm going to go, don't worry about it. Okay. So here's where I'm going to sort of make a leap of faith with you. I don't want to integrate that thing with respect to R because it's going to be kind of nasty. And, we probably could do it using change of variables. Certainly you could do it with like trig sub, but we don't want to go there. So change of variables would probably be your best bet. But even then, after we did it, once we get to the point where whatever value we got, because, the limits are constant, 0 to 2 are the limits for R, then we'd have to integrate sine theta with respect to theta, which would be what? Minus cos. But isn't minus cos when you evaluate it between 0 and 2 pi, since the cosine of 0 is the same as cosine of 2 pi, this would go to 0? Please say yes.
Yeah.
Yes.
So this term, you can argue legitimately that this term does not contribute anything ultimately because of that fact. This term contributes nothing to the final answer unless you consider 0 a contribution. Okay? So we're going to kill him off. Well, I'm not going to bother with him. I'm like, nah, you're dead. Okay, you're dead to me. Then what? Well, I just integrate 2r with respect to r. Okay, I'm just going to worry about that only because, he's going to actually contribute something that'll be worthwhile. Okay, well, what's the antiderivative of 2r with respect to r? Okay, this is not a trick question. Okay. R squared, I feel like it is. Oh, you must mean you're up to something. No, I'm not. Okay. 0 to 2, and I get 4. Okay. And then ultimately you're going to integrate 4 with respect to theta. Okay. So 4 theta going from 0 to 2 pi. Final answer, 8 pi. Yes. And that is exactly what we were hoping for. Why?
It verifies our left and right hand sides.
Exactly. We just thankfully verified, since when we did the left-hand side and we did it by brute force with the line integral and we had to parameterize and all that horrible mess. So I hope that you see that this all works out. Now you may be thinking, well, that Stokes, man, that sucks. But Stokes doesn't usually suck. But as far as this was a little bit messy. But I wanted you to see this example for a number of reasons, because it's a classic Stokes example. And then finally, to kind of wrap this all up, here is something that you can kind of summarize before I get to the meme. Some integration formulas that you've learned from Calc 1 through Calc 3, because you guys have learned an awful lot in my class. Okay, like if I gave you the final exam on day 1, you would have freaked out. Think of all the knowledge you now have, right? I mean, wow, you've come a long way. You actually
Bludgeoning
learned
amount.
some stuff that nobody can take away from you, because that's what education is about. So this is what you learn in Calc 1. You learn the fundamental theorem of calculus, and you know that's pretty basic. And then that we use that to kind of help prove the fundamental theorem of line integrals. And keep in mind, the fundamental theorem of line integrals, which is going to be on midterm 4, you bet your sweet bippy. When are you allowed to use it? You're allowed to use it when your vector field is
Conservative.
Thank you. So isn't it true that if you have a potential function little f and you take the gradient of that little function, by definition, gradients are conservative, right?
Correct.
You don't even have to prove to me they are. They just are. You can just say this on the test Wednesday. Gradients are conservative vector fields. And I won't argue with you because you'll be right. Then what? Shoot, man, just use the gradient if they did give it to you, unless you have to derive it by integrating, and then evaluate your gradient, your potential function between the ending point and then minus evaluate it at the start point. That's the fundamental theorem of line integrals. That will be on Wednesday's exam. Fine. And now the Green's theorem, and that we're just showing you the circulation version. This is the circulation version only. But I'll go ahead and do the flux version so you definitely will know it. How do you know it's the circulation version? One way is they could tell you, like, except the circulation. Or when you look at the line integral, the differential form is m dx plus n dy. That's, boom, circulation form. And so that means your double integral will look like the n dx minus the m dy, which is the same as the projection of the force field onto the unit tangent vector, which is FDR, which really is the same as the double integral evaluated at the curl of that, the two-dimensional curl of that vector field. And then here's the flux version. They don't kind of keep it short. I kind of don't like their flux version because they didn't give you the differential form. They just went, well, you know, the projection of F onto the unit normal vector outward, which is the divergence of F. Okay, that's true, but how would you know you're doing the flux differential form? And you need this for midterm 4, so please write this down. Because when you do that verify, you're going to verify m dy minus n dx. So when I ask you to do a verify for the flux, this is the line integral you're going to do. So you're going to have to parameterize, you know, and get your r, and then get your r prime, and then the dy is the y component of your r prime, and the dx is the x component of your r prime, right? And that is the same as the double integral over the region of the divergence, the two-dimensional divergence of that vector field, dm dx plus dn dy. Okay, so that's the flux version of Green's. Fine. Then what? Last week, we did the divergence theorem, which allows you to compute the total flux over a closed surface, a closed surface making up the boundaries of a solid. And it basically allows you to avoid doing a flux integral and simply do a triple integral, which is great. Except when you're in the world of triple integrals, you have to know how to do rectangular coordinates, cylindrical coordinates, as well as spherical. You think I'm going to give you all 3 on the midterm Wednesday?
Yep.
You bet your sweet Vivi I am. So know how to do that. Well, I never liked spherical coordinates. I don't care. Learn it between now and Wednesday. You were supposed to learn it for midterm 3. Now's a good time. And then finally, now this won't be on the midterm 4, but this will be on the final. And you just did a problem. You're instead of doing a line integral to do the circulation, you go ahead and set up a surface integral, which involves taking the dot product of your curl with your normal vector. Okay, so there you go. That is the summary of chapter 17. Woohoo!
Woo.
Yeah, vector calculus, baby, fun times, right? And kudos to you for making it through. And here's my meme to finish it out. The more complicated the math, the dumber you sound explaining it. Stokes theorem, yeah, that's how if you draw a loop around something, that's the curve sort of at the bottom of the surface, you can tell how much swirly is in it. That's that little paddle wheel spinning, swirling around. Yeah, that's the swirly. And that's what Stokes lets you compute, is the swirly in it.
That's literally what I sound like explaining math to my parents.
Yeah, well, you know, when your mom goes, hey, honey, what'd you learn in calculus today? You could go, well, you know, if you draw a loop around something, you can tell how much swirly is in it by computing, you know, by using the Stokes theorem.
I told him that there's a little gnome helping you whenever you're trying to figure out
Source and sink.
Yeah, source and sink. And they're
Yeah,
like,
if it's the source, the gnome is blowing water out. And if it's a sink, he's sucking down the water.
their minds just went vacant when I said, yeah, the gnome's helping you with the source and sink. They're like, gnomes are in math. I'm like, in a way, yeah.
Well, they are in the Rasky experience class. Okay, folks. All right. So I am officially done with the lecture, and I will say